right, so thermodynamics, sheet 1, thermodynamics, sheet 1. The first problem, we have the following cycles, indicator diagrams. Oh, this is the opposite direction. Must be that way only. See, that's a typo. If there is not an arrow from B to C, how will there be a full cycle here? These are the various cycles executed in the sense shown. We want to find out the cycle in which the change in internal energy is positive. Change in internal energy is positive. Now, is it possible that for a cycle, full cycle, the change in internal energy is positive? No, it's 0 in all cases. Okay. Now, work done, is this positive here? Yes. Why? Clockwise execution of the cycle. Is the work done positive here? Negative. Positive here. Negative here. Right? So which means the heat supplied is positive here, right? Heat supplied must be negative here because work done is negative. Heat supplied is positive here because work done is positive. Heat supplied is negative here because work done is negative. In each of these cases, delta U is 0, right? Oh, in this figure? Okay. So then work done is negative here. If the arrows are like this, then the work done is negative in this case. Anti-clockwise execution, work done is negative. Problem 2. The temperature pressure variation is given as follows: T versus P. A gas goes from state A to state B. This is how T varies as P. Now, do you realize that this is like T proportional to P? Look at the gas equation, PV equal to nRT. P will be proportional to T if V is constant. See? Isn't it? T will be proportional to P only if V is constant, right? That means A to B must be an isochoric process, and therefore the work done in this process must be 0. AB is an isochoric process. Right? Problem 3. We have a process of the following kind: PV, this is a process where BC and DA are isothermal. BC and DA are isothermal. Let's draw pressure temperature graph for this. Option A, let's see the pressure temperature graph, right? and check if option A is right or not. Pressure temperature graph for ABCDA, where BC and DA are isothermal. What is AB? AB is isobaric. What is CD? Isochoric. CD is isochoric, right? Now, when I go from A to B, pressure remains constant, volume increases. So, at constant pressure, temperature will increase. Yes or no? Right? At constant pressure from A to B, temperature will increase. That's AB in the PT diagram. Right? At constant pressure, temperature is increasing because volume is increasing. Look, PV equal to nRT. If P remains constant and if V increases, then T will increase. Isn't it? Right? Okay, that's AB. Now B to C is an isothermal process. Temperature remains constant and volume increases. That means pressure decreases. From B to C, volume increases, PV equal to constant. Volume increases, so pressure decreases from B to C at constant temperature. At constant temperature, therefore, pressure will decrease from B to C. Right? Now, C to D is an isochoric process in which the pressure is decreasing. Do you realize then C to D must go along this? Why? Because see, C to D is a constant volume process. If volume remains constant, then P will be proportional to T. Then the graph of P versus T will pass through the origin, will be a straight line passing through the origin. That's a graph from C to D, a straight line passing through the origin if V is constant, right? And then D to A is an isothermal process. That means constant temperature. That's the PT diagram. That's the PT diagram for this. Clear? Let's draw the VT diagram. Let's draw the VT diagram. Can I wipe this off? VT diagram. See, from A to B, constant pressure process, so V proportional to T. Isn't it? If from A to B, constant pressure, P is constant, so V versus T will be a straight line passing through the origin. Okay. And what is happening to the temperature when you go from A to B? Increasing. From A to B, temperature is increasing. Why? Because P is constant. If volume increases, temperature will increase. Right? So from A to B, you have a V versus T graph, something like this, in which the temperature is increasing. Pressure is remaining constant, volume is increasing, temperature is increasing. V versus T would be a straight line passing through the origin. That's A to B, right? B to C, isothermal process, temperature constant. And what's happening to the volume from B to C? Increasing. Volume is increasing. And if I have an increasing volume, then where will it go? At constant temp, it will go up. It will go up. That means B to C volume increases at constant temperature, isn't it? Yes, sir. Right? Then from C to D, constant volume. C to D is constant volume. Pressure decreases. Constant volume, isn't it? Temperature will decrease. Little clumsy, but let's still. C to D would be like this. Volume decreases. C to D is volume constant, temperature decreases. Because pressure decreases, temperature will decrease. And then D to A is a constant temperature process. So D to A goes this way. Yes or no? See if it matches. A, B, C, D, A. Yes, option B is matching. right? Option B matches. A and B both match, right? So obviously C and D don't match. Right? Problem 4. The PT diagram is known. Hello. The PT graph is known. The PT graph is right? That's a PT diagram. Okay. We want to be able to draw rho v diagram, density volume graph, right? Okay. Now, see, D and A. When you go from D to A, for example, for example, P turns out to be proportional to temperature. P versus T is a straight line passing through the origin. So D to A, this happens, and therefore V must be constant. Yes or no? V must be constant. That means if you go from D to A, if you're talking of the same volume, that means you're talking of the same density. That means points A and D must be at the same rho and the same V. A and D must be at the same rho and the same V. Same volume, therefore same rho, right? Similarly, B and C. See, BC is also P proportional to T. So V equal to constant. So when you go from B to C, volume remains constant. So B and C must be at the same rho and same volume, right? So now when you go from A to B, what is happening to the pressure? It's increasing at constant temperature. Pressure is increasing at constant temperature, isn't it? Therefore volume must be decreasing. That means B is at a lower volume compared to A. B is at a lower volume compared to A. So B and C are at the same point. A and D must therefore be here. B is at a lower volume compared to A, and B and C are at the same rho V state. A and D are at the same state. A, B, C, D, A must be this. This must be the graph. Yes or no? So that makes option B right. Option B right. Now, problem 5, we are talking of a process. Hello, we are talking of a process in which delta U is 0. That means constant temperature. Constant temperature means option B. Option B. Constant temperature means option B, isothermal process. It must be this. It must be this. Option B must be right. Right? Now, VT diagram. There is a line V versus T. If it's a straight line, if V versus T is a straight line passing through the origin, pressure must be constant. Right? And let's say this is a line that represents pressure P2. If V versus T is a straight line passing through the origin, then it represents a constant pressure process. Yes or no? Right? Let's say this is a V versus T graph passing through the origin. It must represent a constant pressure. Let's say it represents pressure P2. This is also some other V versus T graph, and this represents some other pressure P1. All points on this are about a pressure P1. right? We want to figure out which of these is more, P2 or P1. Which of these is more? See, two things. One, algebraically you could see PV equal to nRT, right? Let's say V, if P is constant, V is constant into T. V versus T, V is constant into T, where this constant is like nR by P. The slope of this is nR by P. If the slope is more, isn't it, this constant is nR by P? If the slope is more, pressure is less. If the slope is more, the pressure is less. So P2 must be less than P1. Yes or no? Or the other way you could have looked at it is, at a constant, at the same temperature T, this gives me volume V1, this gives me volume V2. This gives me, so if the volume is more, the pressure must be less at the same temperature, isn't it? V2 more than V1? If V2 more than V1, if V is more, then P must be less for the same temperature. So P2 must be less than P1. Sounds all right? Problem 7. In an isothermal expansion of a gas, select the wrong statement. 1, there is no change in the temperature of the gas. True. That's a true statement. There is no change in internal energy of the gas. That's true. Work done by the gas is heat supplied. True. D, the work done by the gas is equal to the change in internal energy. False. Option D. Right. Now, see, there are times, see in this figure, P versus V graph, which is circular, P1, P2, V1, volume V2. The magnitude, see in this case you have to ensure they are in different scales. P and V are in different scales. Now, if you look at the figure this way, then realize that this length is P2 minus P1, right? This diameter is P2 minus P1. But if you look at it this way, then the diameter is V2 minus V1. That means, now, if you have to calculate the work done, it's this area. It's this area, all right. But you can't say it's pi d squared by 4 or pi this d squared by 4, because this is not the same as this. P2 minus P1 is not the same. What you should do is pi r squared, the area, should have been looked upon as pi r1 because of this P2 minus P1 by 2. That will make it dimensionally correct, because you must have pressure volume to get work done into V2 minus V1 by 2. That's how you should look at it, to make it dimensionally consistent. All that I'm saying is, suppose you had said the work done, area of this, pi by 4, P2 minus P1 whole squared. This is the diameter, pi d squared by 4. Then this is dimensionally wrong, right? Is it not dimensionally wrong? Right? So you must have pressure and volume. So the way you want to write square of the radius is r of this into r for this. That way you will get it dimensionally correct. Yes, absolutely. Pi AB kind of a thing. Matlab, say even if it is not a circle, it will still give you the same area. It will be an ellipse. Pi AB is the area of the ellipse. It will still be the same, right? Problem 9. Problem 9. A fixed mass of an ideal gas undergoes changes of pressure and volume starting at L. Lm straight and then Mn isothermal. Which of the following is correct? Temperature volume graph. You want to draw the temperature volume graph. Which of this is correct? Option B. Yes. See, realize Lm, the process Lm, P is constant. So V will be proportional to T. Yes or no? So V versus T will be a straight line passing through the origin. And if volume is increasing, temperature will increase. V proportional to temperature. So from L to M, V versus T, or T versus V, is it? Okay, T versus V. T versus V. Same thing. Straight line like this. From L to M. And M to N is constant temperature. That's isothermal. Volume increases. Volume increases at constant temperature. Volume increases at constant temperature. Acha, okay. See, L to M is pressure equal to constant, isn't it? This is P equal to constant. Okay. Now look at PV equal to nRT. If P is constant, then T will be T versus V will be a straight line passing through the origin. T equal to some constant into V. T versus V would be a straight line passing through the origin. And since the volume is increasing, temperature will increase from L to M. Is that all right? Problem 10. We have a set of processes PQRS constituting a cycle, PQRS, P constituting a cycle. In some of these changes, work done on the gas is positive, and in others, the work done is negative. Whenever the work done is negative, it is said to be work done on the gas. Work done on the gas, right? Sorry? Work done on the gas is heat supply. No. Gas is compressed. Work done negative, when the volume decreases, work done would be negative. See, when the volume decreases, work done is going to be negative. That's when it is said to be work done on the gas. If the volume increases, work done is positive and work is said to be done by the gas. In which pair of the changes work is done on the gas? That means work done is negative. Okay. Is work done negative in PQ? No, volume increases. PQ, volume increases, work done is positive. Every time volume increases, work done will be positive. Right? Q to R, work done positive or negative? Positive. From R to S? Negative. From S to P? Negative. So in RS and SP, work done is negative and work is done on the gas. That's the rule of the game. Now, we have the indicator diagram PV. A gas is taken from state A to state B along the path state A to state, oh, okay, yeah, now it makes sense. A gas is taken from this state to this state along the path ACB, and along ACB it is found that the heat absorbed is 200 joules. That's given, right? And the work done along ACB is given to be 80 joules. Therefore, in ACB, the change in internal energy is 120 joules. Heat supplied minus work done. That's the change in internal energy from A to B. Now, along the path ADB, heat supplied is 144 joules. Heat supplied is 144 joules. What must be the change in internal energy? Same. If we are talking of the same initial point and the same final point, then change in internal energy does not depend on how you have gone to the destination. If we are talking of the same initial and the same final point, the change in internal energy is going to be the same for all processes that lead you from that point to the final point, right? So if the change in internal energy along ACB is 120 joules, then change in internal energy along ADB must also be 120 joules. It's path independent. And therefore, the work done must be 144 minus 120. That is, 24 joules must be the work done in ADB. Yes or no? Right? Now, from B to A, volume decreases, work done is negative, right? From B to A, work done is minus 52 joules, isn't it? Negative, because volume decreases, work done on the gas means negative, minus 52 joules, right? What is the, now what's the change in internal energy? Minus 120, absolutely. See, UB minus UA is 120. So UA minus UB would be minus 120. Very good. Delta U from A to B would be 120. Therefore, from B to A, it's going to be minus 120. And therefore, what we are seeking is the heat absorbed. Delta Q is going to be minus 172 joules. That means 172 joules is rejected from B to A. If delta Q is negative, means that magnitude of heat is rejected by the system. Are you all there with me on this? If UA is 40 joules, see, if UA is 40 joules, UB must be 160 joules. UB minus UA. So, if UA is 40 joules, UB must be 160 joules. That's internal energy. Yes or no? Now, if UD is 88 joules, so UA we have already computed, UA is 40 joules, UB is 160 joules, UD is 88 joules. We want to find the heat absorbed by the path DB, heat absorbed by the path DB. What is the heat absorbed in dB? See, when you go from D to B, what is the work done? 0. Heat absorbed therefore must be change in internal energy, yes or no? So, from D to B if you go, then change in internal energy is 72 joules. Is 72 joules? UA minus UB minus UD. Work done is 0. Why? Isochoric process, and therefore the heat supplied from D to B must be this plus this, which makes it 72 joules. Yes or no? Right?
Values 40 joules and 160 joules are not respective for only question 13.
Huh?
40 and 160 are respective only for question 13.
No, no, they are all connected.
We can use them in the
Yeah. I mean, this has been obtained on the premise of this, or this has been obtained on the premise of this, so they are connected. Then yes, then. In a process on a system, the initial pressure and volume are equal to the final pressure and volume. If we are talking of the same pressure, same volume, we are talking of the same temperature. The initial internal energy must be equal to final internal energy. Yes, same temperature means same internal energy. The net heat given to the system in the process must be? No. Because see, I could have had a cyclic process. We are talking of the same initial pressure, same final pressure, but work done need not be zero. Change in internal energy will be zero. Why? Because see, I could have had a process like this, for example. A pressure P, a volume V. I could have had a process like this. We are coming back to the same pressure, same final volume, right? So now in this case, delta U is 0 for the process. Coming back to 1, delta U is 0, change in internal energy. But work done is not 0, work done is this area. In this case, for example, work done is positive. If it was driven anti-clockwise, work done would have been negative. But non-zero work done, that's the point. Work done is not 0. And therefore, heat supplied, which is equal to the work done, is not necessarily 0. Pressure volume ABCA, where AB is isothermal. Now, worked option A. So this is all a monoatomic gas, cycle on a monoatomic gas. Work done by the gas in process AB is more than that in BC. No. Area under BC is more than the area under AB. See, area under BC, this area of this rectangle is more than the area under AB. So work done in from B to C is more than the work done in A to B. Nahi kya? Not sure na? At C temperature would be greater. Ha. Right.
So anyways, from A to B work done is negative and B to C work done is positive.
Yes. In this case, what they are seeking is magnitude of the work done. What they are seeking is magnitude of the work done on the gas, by the gas, etc. Net heat energy has been supplied to the system. Hey, for a full cycle ABCA, delta Q, delta U, delta W for the cycle. Delta U is 0 for the cycle, right? And is the work done positive or negative? Positive. The work done would be this area. So work done is going to be positive. So delta Q, which is change in internal energy plus work done, has to be positive. That means there is net heat supplied during a cycle. The net heat has been supplied because delta Q for the cycle turns out to be positive. Temperature of the gas is maximum in state B. Okay. Now first of all, yes, temperature at A and B is the same, right?
Yes, sir.
Isothermal process. Now when you go from B to C, at constant pressure, increase of volume, temperature will increase. So temperature at C is greater than temperature at B. So C is at maximum temperature. Right now? In the process CA, heat energy is rejected by the system. See, when you talk of CA, what is the work done in CA? 0. All points are at the same volume. Work done is 0. and it's a constant volume process. It's a constant volume process. What is the heat supplied? NCV into T minus TC is the heat supplied in a constant volume process. But T is less than TC. T is less than TC. Therefore, this is negative. That means heat must have been rejected. Heat must have been rejected out of this process. Right? Same thing. Yes, you're right. Right? (17) A is true, B is true, A, B, D, D is true. Right? A, B, D. Do you realize that? Shall I explain? Okay. A system undergoes a cyclic process in which, hello, Q1 joules is absorbed and Q2 joules is rejected. Right? That means the work done must be Q1 minus Q2 for a cycle. Work done must be Q1 minus Q2. If 20 joules is absorbed and 10 joules is rejected, that means the net heat involved must be the work done. 20 minus 10 must be the net heat absorbed by the cycle. Right? So work done is this. Right? What is the input to the cycle? Q1. What's the efficiency of the cycle? Q1 by W divided by Q1, which is Q1 minus Q2 divided by Q1, which is like 1 minus Q2 by Q1. Is that okay? In 18, we are going from A to B and then B to C. PT graph, PT graph. Now when you go from A to B, what kind of a process is A to B? Isothermal process. See, temperature, A to B is isothermal. Do you realize that? Temperature is constant. Work done is not 0, right? And work done, is that positive or negative? Negative. Why? Volume see in this case, at constant temperature, pressure is increasing, volume is decreasing, right? V decreases, so work done is negative from A to B, right? In the process AB, heat is rejected out of the system because delta Q is delta U plus delta W, and delta U from A to B is 0. So delta Q from A to B must be negative. Heat therefore is rejected, right? In the process AB, internal energy decreases? No, it remains constant. Isothermal process. In the process AB, internal energy decreases. In the process AB, internal energy increases, decreases. Of course, D, it doesn't make even any sense analyzing because internal energy remains constant. I have a feeling they have typed it wrong. There must have been some BC somewhere which they missed out. Some BCs they have converted into ABs. So, nevertheless, we'll stop here for the day. I want you to attempt all. Yeah, so happy. The subjective problems of sheet 1. I hope you would have taken a plunge into these problems, right? So the first problem, we have a cylinder with a piston and this has conducting walls. This entire arrangement has conducting walls. Temperature of the surroundings is T. That means the temperature of the contents inside the cylinder will remain T, right? The piston, this is the piston, and it's initially at rest, and in equilibrium, That means if P naught is the atmospheric pressure, which acts on this piston, then P naught must be the pressure of the gas for this to be in equilibrium, right? Now the piston is slowly displaced, and they say it contains n moles of the gas. The piston is slowly displaced by a force F. Displaced by a force F. Now I'll tell you why this force ought to be a variable force. The initial volume of the gas is V, and then after a while the volume becomes 2V. The volume of the total thing becomes 2V. Right? We want to find the work done by the external agent in terms of N, R and T. The work done by the external agent in terms of N, R and T. Now, first of all, what's the nature of the process going on inside the cylinder? Isothermal. It's an isothermal process. And therefore, you would expect PV to remain constant. Pressure of the gas into volume of the gas would remain the same all the time, right? Now, if you look at the free body diagram of the piston, see, one of the things that is happening is, as the piston is moving to the right, the volume is increasing, therefore the pressure in the gas is decreasing, right? Therefore the external force must slowly increase so that it maintains equilibrium between the gas contents and the atmospheric pressure. You know what I'm saying? The pressure inside decreases, falls below atmospheric pressure when the volume increases, and therefore to preserve equilibrium of the piston, see, the piston is essentially in equilibrium at all times. When they say it's moved very slowly, that means the piston is essentially in equilibrium at all times. That means the net of all forces is zero. The force because of the gas pressure is decreasing because the gas pressure is decreasing. The atmospheric pressure, the force acting in this direction is remaining the same. Now for this to be maintained in equilibrium, this F in this direction must increase so that the deficit in pressure is made up for. Deficit in pressure of the gas is made up for. Do you all understand this fact? Right? So it's a variable force. It's a variable force acting on the piston. to preserve the equilibrium nature of the piston at all times. This is what it is, right? Shashi? Nahi? How can it be? Pressure will become P naught by 2. If PV is constant, the gas pressure, if the volume doubles, the gas pressure will become half. Yes or no?
Yes, sir.
No. See, the piston, if you really look at the piston, this is the piston. What are the forces acting on the piston? The force because of the pressure of the gas, the force because of atmospheric pressure, and the pressure because of the external force F by area of cross section, right? So when the piston is moved to the right, what is happening to the gas pressure? Decreasing, right? P naught is fixed. So to maintain equilibrium, this F must increase. So it's a variable force. To maintain equilibrium of the piston, a variable force must be brought into picture, right? Or not? Do you all understand this? So by the time the volume doubles, we want to be able to find, by the time the volume doubles, we want to be able to find the work done by the external force. Work done by the external force. Right? Now, the piston starts from rest. Velocity of the piston initially is 0, and the velocity here is 0. Right? Change in kinetic energy is 0. Can I apply work energy theorem on the piston? Just look at the piston. Can I apply work energy theorem on the piston? Yes or no? Right? So, I wish to be able to apply work energy theorem on the piston. This would be, what are the three things doing work on the piston? For the external force, work done by the external force, which we are seeking to find. Work done because of the force exerted by the pressure, right? Work done by the pressure of the gas, and atmospheric pressure is acting this way. P naught into A is the force because of the atmospheric pressure all the time. There is force because of atmospheric pressure, right? So there is work done because of atmospheric pressure. So when the piston goes from this state to this state, this is the work done by the external force, work done by the pressure of the gas, work done by the atmospheric pressure acting leftwards. Right? All of this must be equal to change in kinetic energy of the piston. But what's the change in kinetic energy of the piston? 0. Change in kinetic energy of the piston is 0. Yes or no? Right? Now, work done by the gas. Now, if you really look at the gas, the contents here are undergoing an isothermal change. Work done by the gas during an isothermal change would be nRT log V2 by V1. nRT log V2 by V1 is the work done in an isothermal process by the gas, right? So work done by the gas is going to be nRT log V2 by V1, final volume 2V, initial volume V. So which is nRT log 2 is the work done by the gas. nRT log 2 is the work done by the gas. Yes or no? Now, work done by the atmospheric pressure. Work done by the atmospheric pressure. Look, for the piston, atmospheric pressure is acting this way, right? And displacement is to the right. So work done would be negative, right? Work done by a constant pressure is what? Pressure into change of volume. Pressure into change of volume, but this time with a negative sign. right? Why? Because pressure into change of volume. That's the work done by the atmospheric pressure. Yes or no? Why negative? Because displacement is to the right, force because of atmospheric pressure is to the left. Pressure into change of volume is the work done by, so this is work done by atmospheric pressure, which is minus P naught into 2V minus V, which is minus P naught into V. Hey, but look at this initial state. P naught into V must be nRT, yes or no? P naught into V is nRT, right? So this minus P naught V is like minus nRT, right? Sounds all right? Therefore, this we know, this we know. So can I not find the work done by the external agent? Work done by the external agent, F, is minus the work done because of the pressure of the gas, nRT, and minus nRT log 2 plus nRT. That's the work done, nRT into 1 minus log 2. That's the work done by the external agent. Got me? Problem 2. There is a light container having a diatomic gas, right? Gas moving with a velocity v. Mass of the gas is m and the number of moles is n. Number of moles is n, right? What is the kinetic energy of the gas with respect to the center of mass of the system? See, when I say the kinetic energy of the gas with respect to the center of mass of the system, it's as if when this was not moving, what is the kinetic energy of the system? Right. So when this was not moving, the energy would be the energy in the center of mass frame. That will be the energy in the center of mass frame, right? So the that means the internal energy of this, the kinetic energy in the center of mass frame is the internal energy of this, and the internal energy F by 2 nRT, where F is 5 for a diatomic gas. F is 5 for a diatomic gas. So 5 by 2 nRT is the internal energy, which is also the energy in the center of mass frame, in the center of mass frame, right? Now second, right, the total energy when this moves with a velocity v, then in addition to this internal energy u, it will also have total kinetic energy half m v squared. That's the kinetic energy in the ground frame, right? That will be the second part of the problem. Do you all understand this? Right? Okay. No, I'm saying when this was not moving, what is its internal energy? Right, which is the energy in the center of mass frame. When it's not moving, the energy that it has is the energy as observed by a center of mass observer. Huh? No, it has kinetic energy because of the motion, inherent motion of the molecules. This is kinetic energy. An ideal gas has no potential energy in it. An ideal gas has only kinetic energy because of the temperature of the gas. This is the energy because of the temperature of the gas, motion of molecules of the gas. There is no translation of the center of mass. The center of mass stays put. Center of mass is at rest. So this could also be looked upon as energy in the center of mass frame. Kinetic energy only. There is no potential energy in an ideal gas. Right? And now when it moves, in addition to what it has, the center of mass also has a velocity v and could be imagined to be of mass m. So that energy would get factored in. Right? No, What conservation of energy? Energy is conserved only. Where is it going? Huh? Initial means? No, somebody is providing it an energy to have half mv squared. Where is the loss of energy? This half mv squared is not coming out of the heavens. Some mortal being or mortal entity is providing it this energy. If it was at rest, you know, with this temperature and it suddenly started to move with a velocity v, then that would be magical. That is where you can doubt the consistency or the lack of it of conservation of energy, but otherwise there is no reason to doubt that. Problem 3. So then, these are two non-conducting containers. That means there is no reason for heat to come in or leave the system, right? Right? And they have volumes V1 and V2. This contains a monoatomic gas, and this contains a diatomic gas. F for a monoatomic gas is 3, F for a diatomic gas is 5, right? And they are at temperatures T1 and T2. T1 and T2. There is a stopcock here which is preventing flow because there is pressure differential. Say this one is at pressure P1, this one is at pressure P2, right? There is a stopcock, there is a valve here that prevents flow of gas from one container to another. Now the stopcock, the valve is open and the two gases mix. Alright. We then want to find the final pressure and temperature of the gas. See, when they mix, then there would be heat transfer, which would eventually cause the temperature of the mixture to be the same everywhere. So the two gases would acquire the same temperature. Not only that, the flow would keep taking place till such time that the pressures get equalized. That means the pressure in the two containers will be the same. The temperature of the two containers is going to be the same eventually. That's thermal and mechanical equilibrium. Mechanical equilibrium means same pressure. Thermal equilibrium means the entire mixture would have the same temperature. That's thermal equilibrium, right? That is what you would expect. So eventually the state of the unit would be this. Same pressure, same temperature. Yes or no? Right? Where will the volume go? Right. The volume will be the same. Total, the volume of this will remain V1, the volume of this will remain V2, the total volume will remain V1 plus V2. Right. So we are seeking to find the final pressure and the final temperature. Right? Now, what is the total number of moles here? N1. P1 V1 by RT1. What's the total number of moles of this diatomic gas? P2 V2 by RT2. Right? The total number of moles eventually in this state is going to be, that means this and this put together would be P into V1 plus V2 by RT would be the total number of moles N1 plus N2. Yes or no? right? So out of sheer conservation of mass, we have the final number of moles P into V1 plus V2 by RT, right, equals P1 V1 by RT1 plus P2 V2 by RT2. Conservation of number of moles, equated the number of moles, yes or no? The total final moles, the total initial moles, that will not vanish anywhere, right? Isn't it? Now realize that the total internal energy of the system will remain unaltered. The total internal energy of the system will remain unaltered in this case, right? Why? Because for the two units put together, delta Q is 0, right? Work done is 0. These are fixed boundaries, no net work done. Work done is 0, no volume change, and therefore change in internal energy is 0. Change in internal energy 0 means initial internal energy must be equal to final internal energy. That's what it implies, right? Initial internal energy, energy of this, for example, is going to be what? 3 by 2 nR T1, right? Plus energy of this into 5 by 2 nR T2, that's internal energy of this, right? Acha, N1 and N2, okay, right, N1 and N2, total internal energy, right? And the total internal energy here, see again, it's as if the monoatomic gas that was originally at temperature T1 has now come to a state T. So the internal energy of this N1 moles is going to be 3 by 2 nRT, because isn't it N1 RT 3 by 2 N1 RT. This portion has acquired a temperature T1. Number of moles has not changed, the character of the gas has not changed, so this will remain the same, right? Plus the internal energy of this, all that has changed is this temperature T2 has become T. So 5 by 2 N2 RT, that's equating energy. N1 and N2 you know, so from these two conditions, from this condition you can calculate the final common temperature, because you can plug in the values of N1 and N2, those are known to us, and then having done that you can obtain T from these considerations, plug in that T and obtain the final common pressure, from this by plugging in the value of final common temperature, yes or no? So this one we've this kind of a thing we've applied to a very simple situation, but then down the line you might want to apply it to a little more sophisticated situation, but then this idea should stay put with you, okay? Okay.
Nothing is mentioned, we'll take that the two gases are non-reactive.
Yes. Then it will not be a problem, mechanical thermodynamics problem, it will be more of a chemical problem than a problem on thermodynamics, right? And then you can't come to Malay Khandelwal and solve a problem in which gases are reacting, because the moment gases start reacting, I start reacting because the stench of chemistry bothers me. The stink of chemistry bothers me. Find out the work done in the following graph. It's V naught, is it? And this is 2 V naught? This is P naught. This is 2 P naught. So we have a cycle like this, A, B, C, D. pressure volume, clockwise execution of the cycle, the work done would be simply this area, right? So the work done in ABCD during the cycle would be the area of the shaded rectangle, P naught, V naught, right? Now, we want to be, so we next would convert this graph into a TV graph. This is pressure volume graph. Let's convert this into a TV graph. Now, AB is a constant volume process. See, PV equal to nRT. If V remains constant, okay, okay, V is constant in this case, right? Okay, then I don't have to. So this A to B is a constant volume process in which pressure is increasing, therefore temperature will increase. Temperature will increase. I go from state A to state B with increasing temperature, right? Now, when I go from B to C, that's a constant pressure process. PV equal to nRT. That's for, let's say, the process BC. P is constant, so V will be proportional to T. That means T versus V will be a straight line passing through the origin. Straight line passing through the origin, yes or no? B to C. And since T is increasing, V is increasing, T will increase. From B to C, as V is increasing, T will increase, right? So it's a straight line. Let me make it a little smaller so that it's easier to draw this. This is B. B to C would be like this. Yes or no? Just try and draw it a little better. B to C. T versus V, for constant pressure, T versus V would be a straight line. T versus V would be a straight line, which when produced seems to pass through the origin. And very clearly from B to C, since volume is increasing, temperature is increasing, therefore the graph is headed this way, right? Now from C to D, again a constant volume process, and if pressure is decreasing, then temperature will decrease. Constant volume process, if the temperature is decreasing, pressure decreasing, so temperature will decrease, right? Now D to A, again a constant pressure process, therefore dA, again P equal to constant, so T versus V would be a straight line passing through the origin. We'll have to go from D to A along a straight line. That means dA and origin must lie along the same straight line. dA and origin must lie on the same straight line. So what I do is, let me determine the straight line from O and A. That's D to A. That's the TV graph. That's the TV graph. Right? Similar things I discussed in the last class also. So, do I need to draw the PT graph, or you'll be able to draw the PT graph on your own? Right? Again, whenever volume is constant, PT will be a straight line passing through the origin, and you'll have to use that fact for various processes. Or if you insist, I'll draw the PT graph. No? Okay. The graph will be very similar to this. N moles of the gas undergoing this cycle ABCD. we want to find the work done for a full cycle. We want to find, it will not be the area under the TV graph. It's always area under the PV graph, but not under the TV graph, right? You will have to calculate the work done for each process, right? So then, for A to B, what kind of a process is it? Isochoric. So work done is 0. B to C, what kind of a process is it? Isothermal. Work done would be NR 2 T naught, temperature is 2 T naught into log final volume by initial volume, log 2, right? That's the work done in BC. C to D, what kind of a process is it? Isochoric. What's the work done? 0, right? That's CD. And then DA, what kind of a process is it? Isothermal. Volume decreases, so work done would be negative. So that's going to be, work done in DA is going to be NR T naught log final volume by initial volume, log of half. This will turn out to be a negative number all by itself. Log of final volume 2V divided by initial volume 2V naught, right? So which is like minus NR T naught log 2. So the total work done would be, as you can see, NR T naught log 2 would be the total work done for the cycle. Isn't it? If you add all of them, this is what it turns out to be.
Yes, sir.
What's the heat supplied in the cycle? Net heat supplied to the cycle? Same, net work done. Why? Because change in internal energy in the cycle is 0. So net heat supplied would be the total work done by the cycle. So this will also be delta Q by the cycle. Yes or no? In which of these processes is heat supplied? In which of these processes is heat rejected? Let's check that out, right? Now, what about AB? What kind of a process is it? Isochoric process, right? And the change in internal energy in this process, what would be heat supplied in this process? NCV into final temperature minus initial temperature. Yes or no? Constant volume process, heat supplied as NCV into final temperature 2 T naught minus initial temperature T naught. And it's positive. So heat is supplied here. Right? In BC, heat supplied is work done. Because change in internal energy is 0. Right? So heat supplied is work done, and that's nRT log 2. So heat is supplied in this process. Now if from A to B heat is supplied, then from C to D heat must have been rejected because temperature decreases. What kind of a process is CD? Isochoric process in which temperature is decreasing. Heat involved therefore would be NCV into final temperature T naught minus initial temperature minus T naught. Delta Q turns out to be negative, right? So heat is rejected in this process. Yes or no? What about DA? Heat supplied would be work done. Heat supplied would be work done. And work done for DA we have already calculated as this. So heat supplied would be minus nRT log 2. So heat is rejected in this process. Yes or no?
So BC will be 2 NRT. In B.
Hmm?
BC will be 2 NRT.
Work done. This one.
Work done is
Oh, 2N. Yeah. Temperature is 2 T naught. NR 2 T naught into log final volume by initial volume. And if you add all these delta Q's, that will be the same as sum of all the delta W's, as you can see, right? Now, if I have to calculate the efficiency of the system, what's the cost of running the system? The cost of running the system would be this heat plus this heat would be the cost of running the system. So that's the input to the system. Heat in BC plus heat in BA is the cost of running the system. That's the input to the system, right? What's the output to the system? The total work done. The total work done, the total heat supplied would be the output. So output divided by heat in BA plus heat in BC, that's going to be the efficiency of the system. Into 100 will give you the percentage efficiency. Is that okay or not okay? Where this is A, B, C, D. This is temperature. Can you just tell me the temperatures? These are T1, T2, right? T1, T2, T3, T4 are the temperatures. N moles of the gas, N moles of the gas undergoing this cycle A, B, C, D, A. Right? We want to find the work done in a cycle, given the state, right? Okay. A to B, what kind of a process is it? Isochoric. See, because pressure versus temperature is a straight line passing through the origin. P versus T is a straight line, therefore V must be constant. So V is constant or isochoric, and therefore work done in AB must be 0. Right? B to C is a constant pressure process. Isobaric. Work done in BC must be pressure into change of volume, constant pressure into the volume that changes, which must be NR into change of temperature. Pressure into change of volume would be NR into change of temperature, which is like NR into T3 minus T2. What about CD? What kind of a isochoric? P versus T is a straight line passing through the origin, so V is constant, work done is 0. What about DA? P is constant, right? So work done in DA would be pressure into change of volume, which would be NR into T1 minus T4. NR into T1 minus T4. That's the work done in DA. The total work done would be sum of all of this. The net heat supplied would be sum of all of this. Clear? Problem 7. The PV graph is given in problem 7. A, B, C. This point, right? Okay. That's a cycle, right? And we have 2 moles of an ideal gas undergoing this cycle ABCA. The temperatures of the gas at A and B, TA, is given to be 300 Kelvin and TB is given to be 500 Kelvin. Right? A total of 1200 joules is withdrawn from the sample in the process. That means delta Q in the cycle is minus 1200 joules. Right? We want to find the work done by the gas during BC. We want to find the work done by the gas during BC. Right? Now, realize that if I go from A to B, constant pressure process, right? Work done in AB is going to be NR into delta T. Yes or no? Constant pressure process, NR into delta T. That means 2R into final 200 Kelvin is the change in temperature. So 400 R.
Yes, sir.
Work done in BC, we have to calculate. Right? Work done in CA is 0. Why? Because it's an isochoric process. Now, the sum of the work done would also be the net heat supplied during the cycle. Why? Because change in internal energy is 0 in a full cycle. So, if I add all the work done, then I get 400 R is the net work done, and that must be equal to 400 R plus work done in BC is the net work done, and that must be equal to the net heat supplied, means 1200 R. Right? So work done in BC is minus 1600. Oh, 1200 joules. Okay, so I'm so sorry. Minus 1200 minus 400 R. 400 R, 3200, around 4400. Around 4400, 4500 would be the work done in joules. Right? Sorry? Will A and C have the same temperature? At constant pressure, at constant volume, if the pressure decreases, then the temperature decreases. Right? So obviously not.
So B and C will have constant.
No, why? Who said it's isothermal? Who said it's isobaric, B to C? No, A to B, he's saying B to C. We do not know about the nature of this process, whether it's, huh? It could be, but yes, not mentioned. Nothing can be said. We can't conclude from the data given about the nature of the process BC. Nothing can be concluded. Right? Number 8, I have already dealt with in the class, if you recall.
Yes, sir.
Right? A sample of an ideal gas with degrees of freedom 5, that means the nature of the gas must be diatomic, is heated at constant pressure if an amount of heat 140 joules is supplied to the gas. Find the change in internal energy of the gas, find the work done by the gas, right? Now, the heat supplied is what? N, number of moles, okay, N, we'll assume nothing given, into 5 by 2 into R into delta T. Yeah, N Cp dt. Yes or no? Heat supplied in a constant pressure processes, N Cp, Cp is 5 by 2 into R, that's Cp, isn't it? Right? Or, sorry, 7 by 2. 7 by 2. Because, see, CV is 5R by 2. Therefore, Cp would be R plus Cv, which is 7R by 2 would be Cp. Yes or no? For a diatomic gas? Nahin, confused kya? Heat supplied in a constant pressure process is what? N Cp into change of temperature. Right? For a diatomic gas, Cv is 5R by 2. Right? 5F by 2. Isn't it? F by 2R, F by 2R. Right? F by 2R. And Cp would be Cv plus R. Cp minus Cv is R. So Cp would be Cv plus R. Which would be this. Right? So that gives us nR delta T as 40. nR delta T is 40. Yes or no?
So, but before it was 5 by 2, but we don't write it as 7 by 2.
Sorry?
So, we have written it as N 5 by 2 RT.
No. In a constant pressure process, heat supplied in a constant pressure process is NCP into delta T. Isn't it? Cp is defined as the amount of heat required in a constant pressure process to raise the temperature of 1 mole by unit degree. That's the definition of Cp. So NCP. Cv is 5R by 2. So Cp would be 7R by 2. Isn't it? Confused? So nR delta T turns out to be 40 joules. Clear? We want to find the change in internal energy of the gas. The change in internal energy is always NCV, which is 5R by 2 into delta T. That's the change in internal energy. NCV into delta T is always the change in internal energy. Where 5 by 2 nR delta T is 40. So this into 40. Yes or no? 100. Yes or no? Right? So that's change in internal energy. So delta Q is delta W plus delta U, and you can find delta W given delta Q. We've already calculated delta Q. Delta Q is 140 joules. Delta W we want to calculate. Delta U we have calculated as 100 joules. So delta W would be 40 joules. Clear? So in the next problem, problem 10, we are talking of free expansion. Delta W would be 0, and the entire thing is taking place in an insulated surroundings, so no heat exchange. So delta Q is 0, so delta U will be 0. No, there is never an equilibrium. Precisely. Right. Delta W is 0 in a free expansion. Delta Q is 0 because the whole thing, the free expansion occurs in a insulated surroundings, in insulated conditions, and therefore from first law of thermodynamics, delta U is 0. Now delta U is 0 means what? Temperature remains constant. If temperature remains constant, it would mean that PV is constant. If volume doubles, the pressure becomes half. Pressure becomes half. Therefore, if the initial pressure is P naught of the gas, the final pressure would be P naught by 2. That's the next problem. Three moles of an ideal gas. We are talking of 3 moles of an ideal gas at temperature T equal to 273 Kelvin, initially expanded isothermally so that its volume becomes 5 times. Right? Let's draw the indicator diagram. Right? On the PV graph, we start with a certain pressure, P naught. We start with a certain volume, V naught. And this point has temperature T equal to 273 Kelvin. Right? And the gas undergoes an isothermal change so that the volume becomes 5 times. So pressure will become 1/5. Volume becomes 5 V naught. Pressure would become 1/5. That's an isothermal change, A to B. Temperature remains the same from A to B all along. That's an isothermal change. If then it's heated at constant volume till final pressure becomes equal to its initial value. If it's heated at constant volume, to restore the pressure from P naught by 5 to P naught, it's going from a pressure P naught by 5 to a pressure P naught at constant volume, and the total heat transferred in the process is 80 kilojoules. Find the gamma of the gas. Find the gamma of the gas. That's what we want to be able to do. We want to be able to find the Cp by Cv of the gas. Now, in A to B, what's the heat supplied? That must be the work done. because change in internal energy is 0. So that's 3 RT log 5 log V2 by V1. That's the heat supplied, right? From B to C, heat supplied would be NCV into change of temperature, NCV into change of temperature, change of temperature, yes or no? Yes or no? Yes. Right? Now, look, the temperature from B to C, refer to this, PV equal to nRT. V remains constant. So pressure will be proportional to temperature. So if pressure becomes 5 times, temperature will become 5 times. Right? So what's the temperature at B? T? Temperature at T would be 5T, where T is 273 Kelvin. Yes or no? Right? So NCV into change of temperature therefore would be 4T. 5T minus T, 4T. Right? Now if I add all of this, that is this plus this, 3 RT log 5, heat supplied in AB, plus heat supplied in BC, which is 3, N is 3, 12 CVT into T. That turns out to be 80 into 10 to power 3. Yes or no? T is known to us, 273. So I can solve for CV from this. So once I solve for CV from this equation, I can write CV as R by gamma minus 1. CV can be written as R by gamma, or right here you can write CV as R by gamma minus 1 and solve for gamma. That is what you need to do. Is that okay? So just some calculations involved. Simple otherwise. Clear? In problem 14, you want me to solve 13? It's the area of the triangle, so yeah, half base into altitude. In problem 14, 1 mole of a diatomic gas, 1 mole of a diatomic gas is carried along an adiabatic process from pressure, from a state A, pressure P0, volume V0, to B, which is temperature T0, to T, which is to state B, which is temperature T0. I want to be able to find the volume at B. I want to be able to find the volume at B. I want, right? Now, simple. See, for an adiabatic process, TV to power gamma minus 1 is constant, isn't it? Isn't it? TV to power gamma minus 1 is constant. That means, can I say temperature at A into volume at A to power gamma minus 1 is temperature at B into volume at B to power gamma minus 1? Can that be said? Right? Temperature at A is what? nRT by temperature at T is P0 V0 by nR. That's the temperature at A. P0 V0 by nR is the temperature at A. So temperature at A I can write as P0 V0 by N. N is 1 mole. So by R. Right? That's the temperature at A. Volume at A is V0. To power gamma minus 1. Gamma for a diatomic gas is 7 by 5. 7 by 5. Gamma for a diatomic gas is 7 by 5. Right? So V0 to power 2 by 5 equals T0 VB to power gamma minus 1, which is 2 by 5. So from this you can directly solve for VB. You can directly solve for VB, the volume of the gas at B. One mole of a gas is taken through a process PV cubed equal to constant. Polytropic process, right? From state A P naught V naught to state B where pressure is doubled, right? PV cubed equal to constant. See, if initial pressure state A is P naught V naught to state B, which is pressure to P naught, some volume VB, right? If the pressure is increased, volume will decrease, isn't it? Pressure is increased, PV cubed. If P is increased, V will decrease, yes or no? So the process must be something like this. Pressure increased, volume decreased. State A, where we have volume V naught, pressure P naught, to state B, where we have pressure 2P naught and volume VB. And how do I calculate VB? I can apply PV cubed equal to constant. So P naught V naught cubed must be 2P naught into VB cubed. Can I say this? PV cubed equal to constant. Pressure at A into volume at A cubed is pressure at B into volume at B cubed, right? So that gives me VB equal to V naught by V naught divided by 2 to the power 1/3. V naught by 2 to the power 1/3. That's VB. Clear? Right? Now, we want to find the maximum temperature attained during the process. We want to find the maximum temperature. See, temperature continuously varies from A to B, right? And we want to find the maximum possible temperature for all possible points between A and B. Do you understand the problem? Therefore, first we'll have to identify the point where the temperature is maximum and then calculate the temperature at that point, right? Along this process, which is PV cubed equal to constant. Now, realize PV cubed equal to constant. P can be written as nRT by V. N is 1, right? So RT by V into V cubed must be constant. N is 1, right? R is constant, so TV squared is constant. Yes or no? Yes. So T will be maximum when V is minimum. T will be maximum when V is minimum. Yes or no? Yes. Right? So between A and B, when is V minimum? At B. At B, isn't it? V is minimum from A to B at B. That means at B minimum volume and therefore maximum temperature. And this happens at B. This happens at B. Minimum volume takes place at B. Sorry? Area at? No, go ahead. AB, that's the work done. Area under AB would be work done, right? Now, therefore, all that we need to do is we need to calculate the temperature at B, right? How do I calculate the temperature at B? I know the volume at B. I know the pressure at B. Can I not say temperature is PV by NR? P we know is 2P naught. V we know is V naught by 2 to the power 1/3. N is 1 divided by R. That will give you the temperature at B. By plugging in pressure at B, volume at B, number of moles 1, you can get the temperature at B. This will give you the maximum temperature attainable. You are confused.
I'm asking that without doing all this, we know that as we move higher and higher, we get isotope at higher temperature. So at B, we will get temperature, maximum temperature.
That's the whole idea. Yeah.
Without doing
No. I mean, there could have been something like this and something going this way, etc. No, we can't say. We can't be very sure about that. Let's look at 16. Let's look at so no confusion, right? Fair enough. So we have an ideal diatomic gas, which undergoes a very peculiar process. The process is one, this is a very process specific equation, right? Where the heat supplied is 2 times the change in internal energy minus the work done. That's a peculiarity of the process. That's process intensive equation. Now I want to be able to connect the pressure and volume for the process. Now, no matter what the process is, an ideal gas will always enjoy PV equal to nRT. No matter what the process is, the first law of thermodynamics will still be maintained, right? So heat supplied, even though for the process is this must also be change in internal energy plus work done. That must always be the case, no matter what the process is, right? You know what I'm saying? Change in internal energy plus work done. This then reduces to du equal to 2dW, right? Say 1 mole of the gas, let's imagine 1 mole of the gas. I mean, whether I take 1 mole or n moles, you know, the process specific equation PV to power something, let's say if it turns out, will be the same for 1 mole or 2 moles. That's right. It's not dependent on the number of moles. The process is not dependent on the number of moles, right? So let me take, there would be no loss of generality in taking 1 mole of the gas. If you choose not to, it would not interfere with the process either, right? So change in internal energy is NCV dt. Bolo, yes? Okay, forget it. Let me take n moles, right, into CV. CV for a diatomic gas is 5R by 2. CV is 5R by 2 dt. That's a change in internal energy, right? Work done. Now, work done will always be PdV. For a small change in volume, pressure remains practically the same. Work done would be PdV. Work done would be PdV. Now, what we want to do, we have heterogeneous bunch of entities here, pressure, volume, temperature, everything coming here. What we are seeking to do is, we are seeking to just connect pressure and volume. Let's dispense away temperature. And this is where we take recourse to the ideal gas equation, PV equal to nRT, right? So if I take PV equal to nRT, and that's where you'll realize how n gets eliminated. So if I had taken n equal to 1, it wouldn't have mattered. So d of PV is d of nRT, and if you remember the algebra of differentials, this would be PdV plus VdP is nR dt. So I could have written nR dt as PdV plus VdP. So this is like 5 by 2 nR dt PdV plus VdP. So see, n is not coming anywhere, and it's as if I have taken n equal to 100 or 1 or 200, it wouldn't have made a difference, right? That's what I was trying to communicate, right? nR dt that I obtained from here in terms of pressure and volume, I plugged into this, right? And which then led to twice PdV, right? Let's now consolidate PdVs and VdPs. P dV by 2, right? See, 5 by 2 minus 2, which is 1 by 2 PdV plus 5 by 2 VdP is 0, right? 2 gets cancelled. Divide by PV. So when I divide by PV, I get dV by V plus 5 dP by P equal to 0 when I divide by P, so that the variables get separated, sieved out, volume with volume, pressure with pressure, right? So that I can integrate. Now I integrate. When I integrate dV by V, I get log V. This gives me log P. And then there is a constant of integration, which I transpose to the right hand side, right? This one, this step, I divide by PV. So this becomes dV by V, and this becomes dP by P if I divide throughout by PV, right? And then I integrate both sides. And then there is a constant of integration coming out of each one of them, which I transpose to the right hand side. And then this gives me log V P to power 5 equal to constant, because this 5 can come to the power here, and then log A plus log B, which gives me this equal to constant, right? Isn't it? Or this gives me P to power 5 into V equal to constant. Or if I raise both sides to power 1 by 5, I get P V to power 1 by 5 equal to constant. That's the nature of the process. That's the nature of the process, commensurate with dq equal to whatever was given. Polytropic process. No, you could leave it like this. There is no convention here. There are no hard and fast rules. I mean, if you want to find the polytropic exponent, then the volume, the power of the volume would be relevant, right? N is 1 by 5. So that if you have to calculate the C for the process, then that's going to be R by gamma minus 1 plus R by 1 minus N. N is 1 by 5. Right? See, the options will tell you. I mean, if there are options given like P to power 5 into V equal to constant, then might as well leave it there only. There is an ideal gas that expands from a volume V naught equal to 1 liter. So let me just draw the process. Pressure P naught, volume V naught, 45 degrees here, 45 degrees here. P naught is given to be 1 bar. 1 bar is 1 atmospheric pressure, which is 10 to power 5 Newton per meter squared, right? You know that? Yes. And initial volume V naught is given to be 1 cubic meter, which is 1 liter, which is 10 to power minus 3 cubic meters, right? 1 cubic meter is 1000 liters, right? Along two paths ABC and AC. There is ABC, that's one way to reach C, and the other way to reach C is A to C. There are two paths we are talking of, ABC and direct A to C. The volume here is 3V naught, and what's given is heat supplied in ABC is 600 joules. Heat supplied in ABC is 600 joules. Okay, we want to find the work done in the two paths, the heat transferred along AC, etc. We'll see, we'll figure out. Maybe it will not even matter. Let's see. See, in this case, P naught and V naught are both 1 unit in magnitude drawn on this scale, isn't it? So this lies on P equal to V, making an angle 45 degrees, therefore, right? Now, B relies from A and C. I draw 45 degrees line, a 45 degrees line. Therefore, B must meet, horizontally halfway between A and C. Can you see that? The volume of V must therefore be 2V naught. Can you say that? Isn't it? Okay. All that I am saying is that if I go 45 degrees from A, 45 degrees from C, then B is horizontally halfway between A and C, isn't it? There is no difference. I have to go equally on either side to reach B. What? Nahi? Acha, theek hai. Take it like this. Take it like this. This is A, B, C, right? This is equal to this. 45 degrees, 45 degrees. So this point D would be halfway between A and C, isn't it? Isn't it? Halfway, isn't it? So this is halfway between A and C. This would be halfway between V0 and 3V0, isn't it? Prince Kumar. Got it? Now, the volume at B is 2V0. What would be the pressure at P? See, the pressure here at A is P0, volume is V0, right? At B, this lies on the line y equal to x, because this is making 45 degrees, right? So, if the volume is 2V0, the pressure is 2P0. Yes or no? Tell me. No? I can explain if you are confused. This is a line y equal to x, isn't it? So if this is P0 equal to V0 here, this will be 2P0 equal to 2V0, because P0 and V0 are numerically 1 unit drawn on the scale. So if this volume becomes 2V0, this pressure will become 2V0. So if this is volume is 2 units, 2 liters, the pressure must be 2 bars, because this is a line y equal to x. Have you registered this? Now, the heat, yeah, some, that's all right. That's when we use calculations, but this is drawn on bar and liter scale. This is P, when I am drawing this is P in bars and this is V in liters. This I have converted for the sake of calculations. But numerically this is 1 unit here and this is 1 unit here on this scale that has been drawn. Bar versus liters. That is the scale to which it has been drawn, the PV graph. Right now?
Yes, sir.
Heat supplied along ABC is 600 joules. This is given. Heat supplied along ABC is 600 joules. ABC, heat supplied. Right? Now, can I calculate the work done in ABC? Yes, the area under ABC would be the work done in ABC. Right? This way. PNB housing. Right? In ABC, the work done would be the area of this. Follow, bhai? Which is the area of this trapezium plus area of this trapezium, right? Isn't it? So, work done in ABC, work done in the process ABC, that means from, not in the cycle ABC, but in the process ABC, A to B to C, would be the area of this trapezium plus the area of this trapezium, yes or no? Yes. Right? What's the area of this trapezium? Average of parallel sides into distance between them. So 3P0 by 2 into distance between them is V0 plus identical area here from symmetry. This is an identical area. So into 2. So 3P0 V0. Yes or no? 3P0 V0. For the sake of calculations, I'll have to convert into all SI units. So 3P0 means 3 into 10 to power 5 into 10 to power minus 3. That means 300 joules is the heat supplied, is the work done from A to B and then to C. Right? Therefore, in ABC, what's the change in internal energy? 300 joules. Heat supplied 600 minus work done 300. So that makes it 600 joules from A to B to C. Yes or no? Right? Now, if the change in internal energy when you go from A to C along this process is 300 joules, then change in internal energy from A to C along this process must also be 300 joules, yes or no? Change in internal energy is path independent. So if you go from A to C, the change in internal energy from A to C will be the same as change in internal energy from A to B to C and will be equal to 300 joules. Naina? Is there any confusion? No. Now, work done from A to C. That's easy to calculate, right? Area under this, that means the area of this rectangle, which is P naught into 2V naught, right? Which is 200 joules. Is the work done from A to C? See, P naught is 10 to power 5, V naught is 10 to power minus 3. So 200 joules, and therefore the heat supplied in A to C from first law of thermodynamics would be this plus this, that makes it 500 joules is the heat supplied from A to C. Have I confused you? No, so but then this graph has been drawn, what you see in this graph, which is in bars and letters. But when you do the calculation, you are not obliged to do it in the units presented there. Yes, you will get different, yes, you will get different graphs. It will shift. It will shift. Sorry? No. The scale changes. The facts don't change about pressure, volume, temperature. See, what I could have done is, I could have written this P naught, V naught worked in bar liter. That would have been fine. Write everything in bar liter. And then you convert bar liter into joules. Yeah, the looks won't change. It'll only get scaled up. It'll be similar, not congruent, it'll be similar. You'll get a similar figure, not a congruent figure. No. Those are facts about the gas which will not change. No. Let him understand this. If he has a confusion, let him get past. Yes, that's what I said. It'll be similar, not congruent. Isn't it? I mean, for example, right now, this is 2 units because V naught I have taken in liters. This is 2 units. If I draw in cubic meters, it will be 2 to 10 to power minus 3 units. But again, in that graph, I can take a scale which is of my choice, isn't it? You can draw a graph to a scale of your choice. So then also you will get a similar look, isn't it?
So then that angle won't be 45.
No, that angle will still be 45 degrees. It will get just diminished or enlarged depending on the scale. That angle will still be 45 degrees. Right? Because everything is getting equally magnified. This is becoming 10 to power minus 3. This is becoming 10 to power 5. So, we are having looks that are similar. Looks won't change. Got me? I can. If that's your question, I can. But what if I don't?
According to this graph, P is proportional to V. But that is not possible.
Yeah, but P is proportional to V means temperature is not constant. If P is proportional to V, then temperature is not. If P is proportional to T, then volume is constant. If V is proportional to T, then pressure is constant. But if P is proportional to V, temperature is not constant. Where is it constant, my friend? When did I say temperature is constant? I'll tell you what the temperature here is. Please listen to me. The temperature here, TA, is P naught V naught by NR. Right? Pressure doubles, volume doubles when you go to this point. The temperature here is 4 times TA. When you go to C, the pressure is P naught, volume has become 3 times V naught. So if pressure remains P naught, volume becomes, then this will be 3 times T naught, TA. Where is the temperature constant? No, temperature is not constant, right? So then, if that's your only question, can I draw the PT graph? I can. But do you want me to draw the PT graph? I will. I will. See, now I have taught parabola to you, so I can draw PT, CT, everything. Okay. No, there is nothing physical about P proportional to V. Just like for V proportional to T, P is constant.
Okay, we have like PV to the power minus 1 is constant, so P is proportional to.
If P is proportional to V, that means P is CV. Right?
See, PV to the power minus 1 is.
Yeah, so then what?
That's it. Like, how
Let's draw the PT diagram. Let's draw the PT diagram. A to B. Let me mathematically write the equations first for various processes in pressure temperature. Pressure temperature connection for various processes A, B, B, C and CA, right? AB is this line P equal to, equation of AB is P equal to V. Equation of AB is P equal to V. Yes or no? Right? P, we want to draw PT, right? So V is nRT by P.
Yes, sir.
Right? So the equation of AB in PT is P squared is nRT.
Yes, sir.
It's a parabola, isn't it? T versus P versus T is going to be a parabola. Its axis of symmetry would be P squared equal to 0. Right? That kind of a parabola, isn't it? P squared equal to constant into T is a parabola. Y squared equal to 4AX. Yes or no? Okay. Then for BC, let me write the equation of BC. I know the coordinates of 2 points, right? I know the coordinates of 2 points. So then what would the equation be in P versus V? What would be the equation in P versus V? P equal to P minus 2P naught divided by V minus 2V naught. That's a slope for any PV on this, right? That must be, what's the slope? Slope of this is minus 1, isn't it? Slope of this is minus 1. Tan 135 degrees is the slope of this. So minus 1, yes or no? Yes, ah. Anyways, I'm feeling so low the way we lost today. Huh. So yeah, you need to do something to change the spirit. No, this is right. So what I can do is, this 2P naught is 2 units, this 2V naught is 2 units, right? So then all that I need to do is, I can write V equal to nRT by P. V equal to nRT by P. Yes or no? Right? So I have the equation, PT equation for BC also. I have the PT equation for BC also, right? Yes or no? See, 2P naught will get cancelled with 2V naught because 2 units in magnitude. P is minus V. V can be written as nRT by P. So P squared is minus constant into T. This parabola will open in the other direction because of the minus sign. Oh, sorry. Oh, yeah. So P equal to 4 minus V. 4 minus V. I'm so sorry, I unnecessarily cancelled this. The slope is minus 1, isn't it? Oh, I have written what?
You have taken the exponent.
PT. P versus V. Y is P. 2P naught minus P naught. P minus 2P naught divided by V minus 2V naught is minus 1. What is the problem? I mean, this is not X and Y. In this case, this will be X and this will be Y. So, Sure. So again, you have p squared, t as a quadratic in p, t which will again be a parabola, t as a quadratic in p will be a parabola. This again you need to be able to trace. And then from A to C, what kind of a process is it? P equal to constant. P equal to constant, if I draw the PT graph, will be a line parallel to the temperature axis, will be a line parallel to the temperature axis. Right? You should be able to draw these parabolas now appropriately.
P minus
I can. But I won't. Okay. This equation? Huh?
next line.
Multiply. And then?
So by 4 came over there.
Huh? 2 units plus 2 units. P naught, V naught are 1 unit each. So 4 units. 2 plus 2. V. How did the? Oh, I'll tell you how. The combination of these parabolas would be like this, like this, like this. Check that out. But I wanted you to see that yourself. That is how they will look. This parabola would be like this. This parabola would open this way, and then it will come this way. This is how it will be. This will be P equal to constant for, right? PT will be like this. Got me? This is how it will be look, but this is how it will look, but I want you to check it yourself. From A to B, this parabola. From B to C, this is a parabola wanting to open this way, the other way, because of the minus sign. And then from C to A, a constant pressure line. You should be able to check on these things. Huh? What would be the? This. Yeah, what common area? This would be the common area. Right? Man, was that a question or an assertion? Okay. Right, you're right. An ideal gas is taken through a. Is it all very confusing? No, no? An ideal gas is taken through a cyclic thermodynamic process through 4 steps. The amount of heat involved in the 4 steps are Q1 is 5960 joules, Q2 is minus 5585 joules, Q3 is minus 2980 joules, Q4 is 3645 joules. And the work involved in the various processes, W1 is given to be 2200 joules, W2 is given to be minus 825 joules, W3 is minus 1100 joules, and W4 we need to know. Yes, it's a cyclic process, so net heat supplied must be net work done. So Q1 plus Q2 plus Q3 plus Q4 must be W1 plus W2 plus W3 plus W4. You can calculate W4 from this, isn't it? And what's the efficiency of the cycle? What's the net output? The net output would be the algebraic sum of Q's, Qi's divided by the input, which is right. Now you got it right. Q1 plus Q4 into 100 will give you the percentage efficiency. Thermodynamic cycles, you know, typically, let me tell you, in real life, they are not more than 20% efficient. You won't get a thermodynamic cycle in real life that is like 35% efficient, 40% efficient. No, if you typically you should get like a 20-21%, which is a very efficient cycle. If it's 21% efficiency, the net efficiency is even lower than 21%. See, this is the bare thermodynamic cycle, which is producing, which is taking an amount of heat Q1 plus Q4 and producing right out of the cycle, right from the womb of the cycle, it's producing a work output Q1 plus Q2 plus Q3 plus Q4. But it's not like Q1 plus Q2 plus Q3 plus Q4 is the eventual work output that will get harnessed. This work output straight coming out of the cycle would have to be further processed. Let's say if it's a car engine producing this output, right? Straight out of the engine this output is produced. But in order that it could reach the wheels, there are transmissions in between. So this work output is transferred to the transmissions, which take the onus of transmitting this to the wheels. So then the transmissions, if they are taking 100 joules of energy, it's not like they are transferring 100 joules to the wheels. The transmissions have friction, they have their own efficiency, so some amount of energy is dissipated and they are consumed by the transmission. So eventually only say 80 or 70% of what's produced straight out of the thermodynamic cycle is actually reaching the wheels. So the cycle is producing, let's say, 20% efficiency, and of which it would be excellent if 80% of it could reach the wheels. So which means only 16% efficiency, which again is good efficiency, right? Right. Is that okay? Right. So in 19th, they have this indicator diagram for a cycle. One mole of a monoatomic gas undergoes this cycle. We want to be able to compute the work done by the cycle, and the efficiency of the cycle, given the PV diagram. Okay. Now, so the cycle is executed. Thank you. Such a relief. Clockwise, A to B, an isochoric process. The temperature at A, B, C, D are known. CD is a linear variation of pressure volume, but CD is not an isothermal process. It's just that the points C and D are at the same temperature. They lie on the same isotherm, but the process CD is not isothermal. You know what I'm saying? Now, the total work done and the efficiency of the cycle, that's what we want to be able to deal with. So look at the point A. It's at pressure P0, volume V0, 1 mole of the gas at temperature T0. So can I say P0 and V0 must be related as follows? P0, V0 is RT0 for 1 mole of the gas, right? Now when you migrate from A to B, you are doubling the temperature at constant volume. Therefore the pressure will get doubled. So the point B then is at pressure 2P0. The point B is at pressure 2P0. Clear? Now, when you go from B to C at constant pressure, the temperature is getting doubled. Therefore, the volume must get doubled, right? So, when you go, B is at volume V0, C therefore must be at volume 2V0. Right? Now, when you imagine going from A to D at constant pressure, the temperature is becoming 4 times, so volume will become 4 times. Yes or no? Right? Now, work done would be the area under area enclosed by this cycle? Area enclosed by this cycle, that's a work done? Yes or no? Right? So, work done during the cycle A, B, C, D, A is the area enclosed which is the area of this trapezium. Yes or no? Which is the area of this trapezium, which is average of parallel sides into distance between them, right? This side is V0 units and this side is 3V0 units. Yes or no? This is V0 units, 2V0 minus V0, V0 units, 3V0 units. So 4V0 by 2, that is 2V0 is the average of parallel sides, right? Into the distance between them. The distance between them is P0, right? So into P0. So 2 P0 V0, 2 P0 V0 is actually 2 R T0 because P0 V0 is R T0. So this is actually 2 R T0. That's the work done in the cycle. That's the work done in the cycle. Clear? Now, the efficiency of the cycle. So this is really the output of the cycle. We now need to know the input to the cycle. That means all the processes that involve positive heat supplied positive. That means absorption of heat. They take heat from the surroundings. Clear? Now, if you look at AB, it's an isochoric process, right? Heat supplied in AB is positive because temperature is increasing. So that's N, which is 1, Cp into temperature change, which is T0. NCP into delta T, that's NCV, beg your pardon, NCV. NCV, it's a constant volume process, so heat supplied would be NCV delta T. NCV delta T, that's a heat supplied, right? CV for a monoatomic gases, 3R by 2. For a monoatomic gases, 3R by 2. CV for a monoatomic gases, 3R by 2. CP for a monoatomic gases, 5R by 2. Right? So this is 3R T0 by 2. That's a heat supplied in AB. Now, BC is a, so, right, like this. Clear? Now, what about BC? Isobaric process. Heat supplied would be NCP delta T, right? N, which is 1 mole, into Cp, which is 5R by 2, into delta T, which is 2T0. NCP into delta T, 2T0, right? That makes it 5R T0, positive heat. So this will also be there. Yes or no? Yes, sir. Okay. Now look at the process CD. In the process CD, even though it's not an isothermal process, the initial point and the final points are at the same temperature, and therefore the change in internal energy must be 0. Therefore, all the heat that is supplied must go towards doing work. Now, work done in CD is actually this area. Area under this process, that's the work done in CD, right? Work done in CD, which means average of parallel sides, this is 2P0 plus P0, 3P0 by 2 into distance between them, which is 2V0. So that makes it 3P0 V0, 3P0 V0, where P0 V0 is RT0. So this is 3RT0 and positive, right? So this also results in positive heat. dA, constant pressure, volume decreases, temperature decreases, heat is rejected. Heat is rejected. So this will not participate in the input. This will not participate in the input because heat is rejected from this process, right? So then the net heat, no, not the net heat, the input to the cycle, input to the cycle would be sum of all the positive delta Q's, would be sum of all the positive delta Q's. Positive delta Q's means this is 3 by 2 plus 5 plus 3 RT naught, which is 19 RT naught by 2. That's the input. All the sum of all the positive delta Q's, right? And the output of the cycle is the work done by the cycle, which is 2 RT naught. That's the output of the cycle. The efficiency, therefore, would be output divided by input. That's going to be the efficiency of the cycle. Hmm? Hmm. And therefore, so what? Where? In BC? No, but this 5 RT naught is work done plus change in internal energy. This includes work done, but I have calculated delta Q from independent considerations. Cp into delta T is the heat supplied in a constant pressure process, right? So the efficiency of the cycle is output, which is 2 RT naught divided by input, which is 19 RT naught by 2 into 100. That's the percentage efficiency. 400 by 19%. Roughly 21% is the efficiency. 21% is the efficiency approximately of the cycle. Got me? As a result of isobaric heating, constant pressure, change in temperature that results in a certain process is 72 Kelvin. 1 mole of a certain gas obtains an amount of heat delta Q equals 1600 joules. Find the work performed by the gas, the increment in the internal energy, and the value of gamma, which is Cp by Cv. These are the things that we need to calculate for the gas. Given delta T is this, given N is 1 mole, delta Q is this, we want to be able to calculate, and this happens at a constant pressure process, in a constant pressure process, isobaric. Right? We want to calculate the work done and the change in internal energy for the gas. Right? Now, delta Q in a constant pressure process would be NCP delta T. NCP delta T. Right? Cp is gamma R by gamma minus 1, right? Gamma R by gamma minus 1, that's Cp. Isn't it? Cv is gamma R by gamma minus 1. Cp would be gamma R by gamma minus 1. NCP into delta T. N is 1 mole. And that's given to be 1600 joules. Right? And this gives you an opportunity to calculate gamma. Right after this, you can calculate gamma. Now, once you know gamma, what's the change in internal energy? Change in internal energy would be NCV delta T. Would be the change in internal energy. N is 1 mole. Cv is R by gamma minus 1 into delta T. This could then be calculated. Change in internal energy. Right? Because you have calculated gamma from these considerations. Bless you. Plug in the value of gamma here and you get the change in internal energy. And then the work done would be obviously delta Q minus delta U. That's going to give you the work done. Right? That's what you want to be. Simple calculations, really. 21. An ideal gas an ideal gas whose adiabatic exponent is gamma is expanded according to the law P equal to alpha V. Is expanded according to the law P equal to alpha V, where alpha is a constant. The initial volume of the gas is given to be V naught. As a result of expansion, the final volume in this process becomes eta times V naught, right? What we are seeking to find here is the increment in internal energy, change in internal energy, 2, work performed, 3, molar specific heat of the gas in the process. Molar specific heat of the gas in the process. These are the things that we need to evaluate. These are the things that we need to evaluate, right? First things first, straight away, work done would be integral P dV. V runs from V naught to eta times V naught. Yes or no? Initial volume to final value. This is how you calculate the work done by the gas, right? Undergoing pressure volume changes, isn't it? This P then could be written as alpha V. So alpha V dV. V runs from V naught to eta times V naught, which is alpha by 2 V naught squared into eta squared minus 1. That's the work done. That's the work done. Right? Yes or no? Now, see, this process is like PV to power minus 1 equal to alpha, which is a constant, isn't it? That's what this process is. Polytropic process in which the polytropic exponent is n equal to minus 1, right? The molar specific heat for such a process is going to be R by 1 minus n, means R by 2, plus R by gamma minus 1, R by gamma minus 1, which is CV. CV plus R by 1 minus n. That's how you calculate the molar specific heat for the process, right? Have you forgotten the formula? C for a polytropic process. If there is a process PV to power n equal to constant, then n is the polytropic exponent, right? Then the molar specific heat for the process is R by 1 minus n plus R by gamma minus 1. That's a molar specific CV plus, right? So n in this case is minus 1. So R by 2 plus R by gamma minus 1. That makes it R by 2 into gamma plus 1 divided by gamma minus 1. Yes or no? Now, the change in internal and the work done. The work done we have calculated, change in internal energy. Change in internal energy. Now, change in internal energy is always n, which is 1 mole of the gas, right? 1 mole of the gas into CV into delta T. Okay, so n naught moles, say n naught moles. That's a change in internal energy. NCV into delta T, right? Which is like n naught, CV is R by gamma minus 1 into delta T, which is like T final minus T initial. Right? Which is like n naught RTF minus n naught RTI divided by gamma minus 1. Right? This is final pressure into final volume. This is initial pressure into initial, because nRT is pressure into volume, right? So nR into final temperature is going to be final pressure into final volume. This would be initial pressure into initial volume, right? And what is initial pressure? Initial pressure would be alpha times initial volume. So that's going to be alpha V naught. What's final pressure? Final pressure is going to be alpha times eta V naught. Does it make sense to you? Right? N naught RTF, which is final pressure alpha eta V naught into final volume, right? Eta squared, I'm so sorry, alpha into eta V naught alpha squared. This is what you get. See, final pressure is this, final volume is this. There would be only one alpha. Alpha eta V naught squared. Alpha eta V naught squared. Final pressure into final volume. Right? This is what you get. See, this into this. Alpha into eta V naught whole squared. Minus initial pressure into initial volume. Alpha V naught into V naught, which is alpha V naught squared. Gamma minus 1, which is like a alpha V naught squared into eta squared minus 1 divided by gamma minus 1. That's the change in internal energy. Are you all right with this? There is a TV cycle. Two moles of an ideal monoatomic gas undergoes a cyclic process in which T1 is 1800 Kelvin, T2 is 600 Kelvin, T1 is 300 Kelvin, T2 is 600 Kelvin, T3 is 1800 Kelvin, and T4 is 900 Kelvin. Right? Although, you know, the diagram is drawn inappropriately. T4 is at a higher temperature than T2, but the diagram shows T2 to be at a higher temperature than T4. So it's just that we need to redraw it appropriately, right? So just to be consistent with this data, this is the cycle. This is 1, 2, 3, 4. Now T4 looks a wee bit higher than T2. That seems all right. See, little bit by brute force. 1, 2 and 3, 4 are isochoric processes. As you can see, 1, 2 and 3, 4 are constant volume processes. 1, 2 and 3, 4 are constant volume processes. Now, see, 1, 2, 3, 4, isochoric, right? What's the work done in these processes? Work done in these processes is going to be 0, 1, 2 and 3, 4, right? Clear? 2, 3. What kind of a process is 2, 3? Isobaric, yes. See, T versus V, a straight line passing through the origin will happen when pressure is constant, right? So 2, 3 and 4, 1 are isobaric processes, constant pressure processes. we want to be able to calculate the work done by the cycle. That means we just need to calculate the work done in 2-3 and 4-1, right? Work done in an isobaric process, is P times delta V, right? Which is NR delta T, right? So work done in 2-3 would be N, which is 2R, into final temperature T3 minus initial temperature T2. T3 minus T2, that makes it 1500. T3 minus T2, 1200. So sorry, that's 1200. Right? And work done in 4-1 is NR into T1 minus T4, negative work done. You can see there is decrease in volume, work done must have been negative, right? So which is 2R into T1 minus T4, which is minus 600. So that makes it minus 1200 R, right? Total work done would be this plus this would be the total work done. The algebraic sum of these two would be the total. That means 1200 R would be the work done. 2400 R minus 1200 R, the total work done is going to be 1200 R joules. Is it okay? (23) we are talking of 1 mole of an ideal monoatomic gas. Gamma is 5/3, Cp is 5R/2, Cv is 3R/2, right? You know about the Cp and Cv for a monoatomic gas, right? And this undergoes a process P equal to alpha root T. Alpha is a constant, P equal to alpha root T. We want to find, number one, when the temperature increases by 50 Kelvin, we want to be able to find the work done, 2, the molar specific heat of the gas. These are the two of the process, molar specific heat of the process and the work done. These are the two things that we need to find here. Now, realize that P is alpha root T. Right. This T I can write as PV by NR. Right? N is 1 mole, that's given, right? Okay. So this could have been written as P to power half into V to power half equal to alpha by root NR, which is a constant. Which means PV is a constant. P to power half, V to power minus half. Sorry. P to power half, V to power minus half. That means PV to power minus 1 is a constant. Therefore, the polytropic exponent is minus 1. And therefore, the molar specific heat for the process is going to be R by 1 minus N. That means R by 2 plus Cv. Cv is 3R by 2. So that makes it 2R. That's a molar specific heat for the process. Right? Now, what's the heat supplied therefore in the process? N into molar specific heat for the process into change of temperature. Right? That's the heat supplied in the process. N is 1, C is 2R as we computed, delta T is given to be 50 Kelvin. So that makes it 100 R joules. 100 R joules is the heat supplied. Yes or no? Right? Change in internal energy is always going to be NCV delta T. Cv is 3R by 2 into 50. That makes it 75 R. So work done must be delta Q minus delta U, which is 25 R. roughly 207 joules. R is 8.3, so roughly 207 joules, right? (24) There is an ideal diatomic gas. Diatomic gas means gamma would be, CV would be, CP would be, right, right, and it undergoes a process in which it's found that its internal energy, absolute internal energy, right, is some alpha times root V. Alpha times root V is its absolute internal energy, right? Alpha is a constant. We want to find the work performed by the gas, the molar specific heat for the process, given that the change in internal energy brought about is 100 joules. Given that the change in internal energy brought about is 100 joules. Such is the process, right? Now, realize that U, absolute internal energy, would be, let's say, N moles CV into T. Change in internal energy is NCV into delta T, but absolute internal energy is NCV into T. That's equal to like alpha times root V, right? But PV is nRT. So NT would be PV by R, NT would be PV by R. Is alpha root V? Therefore, CV, R, alpha, these are all constants. And this gives me PV to power half equal to a constant. Polytropic process, therefore, with N equal to half. Therefore, the molar specific heat for the process is R by 1 minus half plus CV. CV is 5R by 2. Yes or no? So that makes it 2R plus 2.5R. That makes it 4.5R is the C for the process. Right? Now, delta U is given to be 100 joules. Right? That means N CV. CV is 5R by 2 into delta T is 100 joules. Is 100 joules, right? So that makes NR delta T equals 40. NR delta T then becomes 40. Yes or no? What we are seeking to calculate is, number one, the work done. What is the heat supplied? Heat supplied would be NC into delta T, isn't it? NC into delta T is the heat supplied, which is like a NC, which is 4.5 R into delta T. But NR delta T is 40. So NR delta T 40, 40 into 4.5, 180. So heat supplied is 180 joules. Change in internal energy is 100 joules. Therefore, the work done must be 80 joules. Heat supplied minus change in internal energy, that's 80 joules. That's the work done. Yes or no? Delta Q we computed from molar specific heat for the process, NC delta T, C delta T, and NR delta T we had obtained from internal energy considerations. That makes it 40. So 40 into 4.5, that makes it 180. And change in internal energy, initially prescribed 100 joules. Therefore, the difference of these two will give me the work done, 80 joules. Right? we have a cylinder piston arrangement, a movable lower cylinder and a movable upper cylinder, enclosing a gas within a height h of uniform area of cross section of the cylinder being A. A is given 27 square centimeters. The gas initially is at NTP, that means atmospheric pressure, and 273 Kelvin, right? So if P naught is atmospheric, which is outside, atmospheric pressure, then the pressure inside initially is P naught, and temperature initially T naught is 273 Kelvin, right? Yes or no? And there is a spring attached, K. Okay. Now, the lower cylinder, the lower piston is pushed up by an amount h by 2. The lower piston is pushed up by an amount h by 2. And it is observed that the upper piston, when this moves up by an amount h by 2, it's found that the upper piston moves up by an amount h by 16 to restore equilibrium. Right? So we need to calculate h, taking gamma for the gas as 1.5. It's an adiabatic process. This whole thing is insulated. Therefore, there is no exchange of heat with the surroundings. So the process assumed the pressure volume changes inside the cylinder take place according to adiabatic considerations. Adiabatic considerations, right? We want to find, once this happens, once fresh equilibrium, mechanical equilibrium is attained, we want to find the h of this arrangement, right? Okay, so in a final state, what really happens is, in a final state, this is what transpires. Realize that the h of the gas would now be, from h, there was a decrease by an amount h by 2, so minus h by 2. And then there was an increase by an amount h by 16, so plus h by 16, yes or no? So that makes it 9h by 16. That makes it 9h by 16, the final height. Yes or no? Because of this, it decreased by an amount h by 2. Because of this, it increased by an amount h by 16. So that's the final height of the enclosed gas. Right? And say Tf is the final temperature. Right? Now, what are the forces acting? Let me look at the free body diagram of the upper piston. Let me look at the free body diagram of the upper piston. Clear? See, one, there is pressure because of the spring force. The spring force is kh by 16 acting downwards on the piston, and the pressure because of the spring force is going to be kh by 16a. Is going to be the pressure because of the spring force. And there is pressure because of atmosphere, P naught. And then, in the opposite direction, there is pressure because of the gas. Under the influence of these three, the piston is in equilibrium. Therefore, this gives us an opportunity to calculate PG. Therefore, the final pressure can be obtained as PG, taking care of P naught plus kh by 16a. That's the final pressure, right? Now, between this state and this state, I'm going to deploy PV to power gamma equal to constant. We are going to deploy PV to power gamma equal to constant. Adiabatic process. Initial pressure inside P naught atmospheric. Now the volumes are proportional to the heights. So volumes can be replaced by the heights, isn't it? Yes or no? So essentially we are going to take pressure into height to power gamma equal to constant. Pressure into height to power gamma equal to constant, right? Because volumes are proportional to the heights, Prince. Okay. Final volume is A into final height, area of cross section. Initial volume is A into initial height. Right? So if I say PV to power gamma equal to constant, that means let's say P into A into H to power gamma equal to constant. That means pressure into height to power gamma equal to constant, because A is a constant. So pressure into height to power gamma equal to constant is an equivalent statement of PV to power gamma equal to constant. Yes or no? What? Okay, that's all that I was saying. So initial pressure, confused kya? Tell me. Area of cross section. This is the area of cross section of the cylinder. This area. This kh by 16 acts over an area A. That's the area. Area of cross section. It's a cylindrical portion. The area of cross section is the same. Pi r squared. Right? Is the area of cross section. So P naught into initial height, which is h, to power gamma, equals final pressure, which is P naught plus kh by 16a, into final height. Final height is 9h by 16 to power gamma. Yes or no? Right? Now gamma is 1.5, so 9 by 16 to power 1.5 means 3 by 2. That makes it 27 by 64. Yes or no? Isn't it? So this I can write as h to power gamma gets cancelled. P naught equal to P naught plus kh by 16a into 27 by 64. Right? Tell me, what's the confusion? And therefore you can solve for h straight out of this. 64 P naught by 27 minus P naught, 37 P naught by 64 is kh by 16a. Right? Finish. This is how you calculate the h. Now the final temperature. Have I confused you? No? Adiabatic process, TV to power gamma minus 1 is a constant. Right? So initial temperature, instead of volumes, I will write heights. Right? So initial temperature T naught, which is 273 Kelvin. Initial volume replaced by the initial height, which is h to power gamma minus 1 means 0.5. Gamma is 1.5, so it's 0.5 equals final temperature TF into final height 9h by 16 to power half. 9h by 16 to power half. Three by 4. So TF is going to be T naught into 4 by 3. 91, 364. 364 Kelvin. T naught is 273. Right? Is that all right? Clear now? (26) A gas is undergoing an adiabatic process. At a certain stage, say the pressure volume diagram for an adiabatic process is like this. At a certain point where its pressure is P naught and its volume is V naught, okay, it's a VT graph that's given. So sorry, what they're talking of is not a PV graph but a VT graph. Let me just see, in a VT graph also TV to power gamma minus 1 is a constant. Right? Right? So if volume increases, temperature decreases and vice versa. Right? So let me draw the VT graph. the slope at a certain point A, when the volume is V naught, when the temperature is T naught, is given to be M. That means the slope of this means slope of the tangent. Slope of the graph means slope of the tangent drawn at that point. That means slope of this, right? Magnitude of the slope of this is given to be M. See, the slope of this is actually negative. You can see that it has a negative slope, but the magnitude of the slope is given to be M, right? And the slope at any point is given by dV dt. dV dt at volume V naught and temperature T naught, volume V naught and temperature T naught. That's magnitude of this slope is given to be M. Magnitude of the slope is given to be M at V naught T naught at the point P, B, A, at the point A. That's given to be V naught. Right? That means, see, if, and dV dt is negative, dV dt is negative, as you can see. As temperature increases, volume decreases, so dV dt is negative. Therefore, mod of dV dt would be minus dV dt. If a number is negative, if A is negative, then mod of A would be minus A. Yes or no? Right? What? So minus dV dt at V naught T naught is M. Yes or no? Given this, we want to be able to calculate the Cp and Cv. We want to be able to calculate the Cp and Cv. Now, the process is adiabatic. Therefore, change in internal energy plus work done will be 0. Right? Change in internal energy is NCV dt. Say 1 mole of the gas, NCV dt. Right? Work done is PdV. That's 0. Therefore, can I say Cv would be at P equal to P naught? See, if I take dt and dV from this point, then that's like the pressure here is say P naught. Then can I say it's going to be minus P naught dV dt?
Yes, sir.
But dV dt is minus M. dV dt is minus M. So this is like P naught into M. But P naught is what? P naught is RT naught by V naught, right? Into M. Yes or no? Now if Cv is known, Cp would be Cv plus R, etc. What? Cp and Cv, their values will not depend on the number of moles. Do you understand that? It's going to be the same for any number of moles. Will Cp of a gas change if you take more moles of the gas or less moles of the gas? So calculate Cp and Cv based on 1 mole. You will get the same thing. Will the slope of the graph change? Then slope of Pv to power gamma, slope of Tv to power gamma minus 1, that's not going to change based on the moles. The slope will remain the same. Got it?
Yes.
Okay. For an ideal gas, the molar specific heat is given as, in a certain process, for a certain process, 3A T squared. The molar specific heat for a certain process of an ideal gas is given as Cv plus 3A T squared. We want to find the T versus V variation for the process. We want to be able to find the T versus V variation for the process. Yeah, A of course is a constant. A is a constant. Right? Now, let me take 1 mole of the gas. Now what's the heat supplied for a change of temperature dt? Heat supplied for 1 mole for a change of temperature would be C dt. That's going to be the heat supplied, yes or no? Right? But that's equal to Cv dt plus 3a t squared dt. This is the heat supplied C dt. C dt is Cv dt plus 3a t squared dt. Clear? Are you all right with this? Now, Cv dt for 1 mole is always change of internal energy, is always change of internal energy. Cv dt is always change of internal energy, isn't it?
Yes, sir.
And therefore, 3a t squared dt would always be the work done for the process. This must be the work done for in the process. Yes or no? Therefore, the statement is dW, the work done is 3a t squared dt. That's the work done. Yes, work done would always be pdv. Now we want to connect T and V, therefore we want to eliminate P precisely. So P I could write as nRT by V. I have taken 1 mole, so RT by V. So this I could have written as RT by V dV. Right? So which means now I can say 3a T dV dt is R by V dV. I could say this. This t gets cancelled with this t. 3a t dt is R by V dV. I then go ahead and integrate. Right? So when I integrate, I get 3a t squared by 2. 3a t squared by 2. What? Equals R log V plus a constant of integration. Yes or no? Or I can say, let me bring this R here. Right? I can say log V minus 3a t squared by 2r equal to a constant. I just transpose log V minus this constant on that side is a constant, and therefore log V, this I can write as log e to power minus 3a t squared by 2r. Yes or no? Can I write this? Tell me if you understand this.
Yes. Yes.
No? No? Didn't? No? Okay, think of it here. X can be written as log of e power x. If x is a, right? Can I do this? Yes, x is this mal. Log e power x. Got me, no? Now log a plus log b is log ab. Which is log v e to power minus 3a t squared by 2r is a constant. And therefore, if the log of this is a constant, therefore this must be a constant, v e to power minus 3a t squared by 2r. That must be a constant. That's the process. That's the v versus t variation. That's the v versus t. It's not a polytropic process. It involves an exponential. It's not a polytropic process. '28. What we have is work versus delta T for three things. One of them is temperature change delta T for an isobaric process. 2, 1 mole of argon adiabatic change, work done in an adiabatic process. 3, 1 mole of nitrogen adiabatic process. These are the three things. We want to map them onto this graph. Which one represents what? That's what we want to figure out, right? We'll take 1 mole of this gas also. So now, in an isobaric process, what's the work done in an isobaric process? N R delta T, N say 1 mole of the gas, R delta T. Work versus delta T would be a straight line with slope R. Work versus delta T is going to be a straight line with slope R. Okay. 2. The work done in an adiabatic process is magnitude of the work done R delta T by gamma minus 1. Magnitude of the work done. See, work done is negative of the change in internal energy, right? So which is R by gamma minus 1 delta T for an adiabatic, and the magnitude of the work, this is all magnitude of the work done, would be R by gamma minus 1 into delta T. Yes or no? Yes. So then for argon, gamma is 5 by 3 monoatomic gas, right? So this makes it work done is 3R by 2 delta T, right? For nitrogen, all that changes is gamma is 7 by 5. So work done is going to be 5R by 2 delta T. That's the work done. Now, of these, which has the least slope? This 1. So 3 must be actually 1, least slope, right? Which has the maximum slope? 3. So this must be 3 and this must be 2. This is the mapping. The maximum slope is 5R by 2, that's for nitrogen. So this is the nitrogen adiabatic, this is argon adiabatic, this is isobaric. Problem 30. A gas is transferred from state 1 lower volume to state 2 higher volume. PV diagram, state 1 lower volume to state 2 higher volume. In two ways, isocore followed by isobar or isobar followed by isocore, right? So the first one, isocore followed by isobar. There are two things. I'll just tell you, there is another possibility of the relative location of 1 and 2. 1 and 2 could be like this, or 1 and 2 could have been like this. 1 could have been here, 2 could have been there. These are the two possibilities, right? Let me examine this possibility first. Isocore followed by isobar. Isocore followed by isobar. That's one, A. Or it could have been isobar followed by isocore. This is B. If there is a supply constraint, that means if there is an issue which involves austerity of energy, in the sense, we don't have enough energy, we want to use a process in which the energy consumed is less, right? Then which of the two should be accepted, A or B? See, whether I take A or B, the change in internal energy is the same. Same. In which case is the work done more, B or A? B. Work done in B is more than work done in A. Therefore, the heat supplied in A must be more than, heat supplied in B must be more than heat supplied in A. Therefore, A should be preferred. Therefore, A should be preferred in this case, because A requires less amount of heat to be executed than B. In B and A, same amount of change of internal energy, but more work is done in B compared to A. The work done in A is simply this area. In B, the work done would be a bigger rectangle, right? Therefore, A should be preferred because it requires less amount of heat. You have a question? Yeah, now I'm coming. If this is the case, then A should be preferred. If this is the case, isobar, isocore followed by an isobar, which is A, or isobar followed by an isocore, which is B. Then of course again the same change in internal energy. In A, work done is more than that in B. Therefore, the heat requirement for A should be more than heat requirement for B, and therefore B should be preferred in this case. In this case, B should be preferred. If that's the case, then A should be preferred. Huh? If this is the case, then this is correct. If that's the case, then that is correct. Huh. All right, 31. Now we have Cp and Cv for a certain gas that is temperature dependent. That's given. Say Cp is given as A plus Kt and Cv is given as B plus Kt. A, B, K are constants. T is the absolute temperature. We want to show that for this, if this gas with Cp and Cv given as a function of temperature, if this undergoes an adiabatic process, then T to the power B, V to the power A minus B, E power Kt must be constant. For an adiabatic process in which Cp and Cv are functions of temperature, this must be constant. This must be constant, right? Now, if it's an adiabatic process, dq, which is heat supplied, work done plus change in internal energy, that must be 0 anyways, no matter how Cp and Cv vary, right? Work done is PdV, du is, let's say for 1 mole, Cv dt, that must be 0. P I can write as RT by V. Cv I can write as B plus Kt. Yes or no? Or dt, there is dV. Or R by V dV, I divide by T so that T flushes with these members, is B by T plus K dt. That must be 0, right? Integrate both sides. R log V plus B log T plus Kt must be 0, must be a constant of integration. Or log v to the power r plus log t to the power b plus log e power kt must be constant. Yes or no? Kt can be written as log of e power kt, right? Or log v to the power r t to the power b e power kt must be constant. Or we have, right, absolutely. See, Cp minus Cv will still be R, and therefore A minus B is R, right? So this R I write as A minus B, this R I write as A minus B. So V to power A minus B into T to power B into E power kt must be constant. That's the process.